Okay, I guess I would like to get started. Welcome everybody online and here in the auditorium for today's JHU. I'm a JHU Space Telescope person, so I defaulted to JHU, to our JWST community webinar today. My name is Bill Blair. I'm a longtime scientist in the community here and have a lot of ops experience, and so I act as sort of a liaison between the science user community and tool developers for the proposal planning system. And today I'd like to tell you about two different kinds of tools that should be useful to you as a potential proposer for JWST, some target visibility tools that are just about to be released to the public with documentation, and also the JWST flavor, as I called it, of the Astronomer's proposal tool. Okay, thank you. And I'm not forwarding. What do I need to do to? Yeah. Every once in a while we have this little glitch. Pardon me for one moment while we and there we go. Okay. So many of you will no doubt be familiar with the HST version of the APT, and I just wanted to highlight the fact that it is a single tool and it works for both missions now, for HST and JWST. I'll show you how you select one or the other of those as we go into the demo part of this. And there are many of the general kind of GUI interface characteristics that are quite similar between the two flavors of this, and I'm going to try to remember to point, if you can see my little pointer moving on the screen with the mouse so that those online can see as well. But basically things like the look and feel of the tool, the GUI interface, the way you enter investigators or targets, those are all pretty similar between the two. Aladdin visualization is there for both tools. But then there are a number of differences that are caused as much by the difference between the missions as anything else that will affect the way you enter observations and process them in APT. And I'll try to just touch on some of I'll try to focus really on the JWST differences today, but I think you'll get it, if you're a new user, you will still get enough of the flavor of the tool to be able to function in it without a primer on that specifically. I was just showing here, by the way, this is the toolbar at the top of APT, and I'll show you a little bit about how choosing these different selections up here affects the display in a little while. I'll just point out here that there is a button on the upper left underneath that toolbar that says New Document, and when you use this pull-down menu, that's where you can say New JWST Proposal, or you can say New HST Proposal. So that's how you select. One of the main differences between the two missions is the way we expect proposers to put in effectively executable programs initially for JWST. This has been called single stream approach. The idea here is to speed up the processing of accepted proposals into the actual mission timelines, but it does drive a lot of what we need to do in APT to make those proposals streamlined. And we're trying to put as many tools in place as we can to help users do this job up front. That is to say, basically put in as close to complete proposals as possible right up front. So to do this, basically things that happen in HST land well after even the phase 2 process and downstream from that to check the schedulability and look at guide stars and so forth, that is all done up front in APT by the user before they submit. If there are problems, there are diagnostics and tools within APT, error messages and warning messages that guide the user to try to handle and remove the errors that will pop up from time to time in APT. Now, the single stream approach doesn't work for everything, and we know that. We're trying to be cognizant of that. Obviously, something like a target of opportunity proposal where you don't know the details of your target, you can't put in up front, and so there will be a mechanism to put in that kind of a proposal with placeholder observations and then worry about the details later on after acceptance. Another variety of that will be the near-spec multi-shutter array proposals, the spectroscopy proposals that need to know the details of the position angle on the sky that the observation will be made before they can provide the details for the planning. Again, there will be a phase 1 version of this where you have to put in prototypical observations and then put the details in later. Many of these proposals will require, for instance, near-cam pre-imaging, and users will have to get that data and then actually work with that to make their near-spec observations schedulable to the system. And so those will have to have sort of a, for lack of a better term, sort of a phase 2 to the process. In cycle 1, since again APT is still being developed and new users to the system will need some time to learn the tools and whatnot, it's quite possible that the Science Mission Office will decide later this spring whether there are additional large or complex programs that they will allow people to cut corners on in cycle 1 while everyone, including us, learns the new system, but that is a TBD at this point. Okay, so a big difference here also between the missions is just the visibility of targets. Of course, Hubble very naturally fell into this mode of using the orbital viewing period as the natural yardstick. You would get so many orbits of time with Hubble, and then you would craft your observations and oftentimes spend a lot of effort optimizing the use of every second of orbital viewing time you could in APT to get the HST orbits as efficient as possible. For JWST, because of its orbit, we don't have orbital viewing periods. It's just time on the sky. How much science time do you need, and what are the overheads? And so you specify your observations, and there's really relatively little tweaking that the user can do to change that. You just say, this is what I want to do. APT knows about the overheads in the background and totals those up on your cover page. And then there's a process called smart accounting that you should run toward the end of your proposal process that takes a pass through and makes sure that the overheads that were put in as the proposal was developed, they will be a little bit out of sync with what the most efficient overheads are, and this smart accounting step is intended to go back and recover those extra overheads that happened as you were building your proposal. So this is called an event-driven way of scheduling as opposed to the orbital viewing period model, and that drives a lot of what you will see in the JWST part of the APT observation templates and GUI. Okay, the last point down here is just that observations from your proposal, of course, are not done as a block. They will be interleaved with other activities, other science programs, other spacecraft activities, and so forth. And so this job of estimating the resources is difficult because here we have to look at a proposal and give you a resource estimate when in reality those will get scheduled out in a timeline with lots of other activities and whatnot. And it's smart accounting is also still being developed to its highest capability to make that estimate as accurate as we can possibly make it. Okay, so in APT, when you get in to the GUI, you will see, and I'll demonstrate this in just a few minutes, that observations are entered in templates. Basically, once you select an instrument and an observing mode, which is the template definition, then you only see the specific parameters that are needed or allowed for that mode. And so you don't have to sort through all the options that are not relevant for that mode. That's called an observation template approach. And so once you've figured out your observation template and specified your observation, much of the rest of the work is done by APT. Again, this is part of the strategy to make it as simple as possible, straightforward for people to specify full executable observations up front in the initial submission. So this is a key part of this single stream approach. Now, you should be aware that what the observer puts into APT are observations, and if those observations need to get broken up into visits, this is something that the APT tool does internally. And visits, the reason that's important to you is that visits are the basic scheduling units for JWST. And so an observation that has multiple visits in principle will not execute altogether unless you tell APT that this set of visits has to execute together. And there are exceptions to that. Mosaics naturally get put together into one observation and don't get broken up unless absolutely necessary. But other multi-visit observations don't necessarily execute all the visits simultaneously and in order. But the visit is the scheduling unit. The observation is what the observer actually specifies in the template. And again, just to highlight that it's very important to run the smart accounting at the end of the proposal process to make sure that the overheads have been handled as efficiently as APT knows how to do it. Okay, so like I said, much of the heavy lifting is done within APT, and actually within APT, a lot of the heavy lifting is done by the section of the tool called the visit planner. This is the thing that looks at the schedulability of your observations in detail. By schedulability, I mean not only just the visibility to the observatory as a function of time, but also the guide star availability as a function of time. And then if you have placed any special requirements on the observations, for instance, that place timing links or position angle links between observations and that sort of thing, this step in APT tries to validate that all of that is indeed doable by the observatory. And you will see green checks on things that pass that, and things that don't pass that get red X's, and then you have to resolve the errors, the red X's, before you can submit the proposal. So the visit planner also provides other diagnostic information. I'll try to show you some of that today. I don't have enough time to really go through all the details. I'll just be touching on some things that kind of point you in the right direction, and we'll leave it to the user to experiment and play with APT. It is intended to be a fairly intuitive tool as much as possible. I'm sure there will be questions and things as you go along, but mostly by clicking and looking at pull-down menus and then referring to documentation that's available at the user documentation site, you will be able to figure out a lot of these things on your own. Again, that's part of the strategy of this single stream approach, is helping you get answers to your questions efficiently. So there are two kinds of feedback that you'll see, errors, red X's in APT, and warnings, which you'll see a little caution sign. And just to highlight, errors are things that need to be resolved prior to submission. Warnings are really there for your benefit and don't necessarily mean there's a problem, but they're things that you should look at. And before I do the demo, just a few other loose ends. I wanted to mention, of course, visualizing your observations on the sky through the Aladdin interface is something that's there for HST, and that is there for JWST as well. I would say that I think it's fair to say that there are still updates that will make that much more usable for people. For instance, I'll show you in my example today that the NIRCam field of view, which is rectangular and has two short wavelength detectors, all you see is one big rectangle on the screen. You don't see the detector gap yet, that sort of thing. Those kind of things are going to come along, hopefully, in future versions of APT, and it'll be a lot more obvious for details like that. But the functionality is there. Prototype fields of view for all the instruments are there at this point, and we just hope to make them better with time. As with HST, again, you can get target confirmation charts to make sure your position is where you want it to be for each target. There is an option for loading target lists in bulk form as opposed to individual target entry. As with HST side, there's the ability to duplicate observations, which is a really handy thing to be able to do if you're looking at multiple targets that are basically the same, except for maybe the details of the target itself and the details of the exposure parameters. You can duplicate an observation and then just change the things that need to be changed. So that's a handy thing to have. And also, I want to say a word about parallel observations in APT. Coordinated parallels in the modes that are shown here in the table are expected to be supported for cycle 1. The version of APT that has just been released does have the capability for adding parallel observations, coordinated parallel observations. As a matter of fact, it makes it very easy, relatively easy to add coordinated parallel observations. And just a caveat I wanted to mention here is that because of data volume considerations, it's not clear that we can just go hog wild on adding mosaics without driving the data volume limits of the observatory, to the point that, for instance, people adding a lot of mosaic observations could actually make it impossible to schedule some primary science that otherwise would be scheduled because the resource has been used up by parallel observations. We obviously don't want parallel observations to drive the primary scheduling of the observatory. So it's a limited resource, and there are policy statements out there to this effect that it's not just being used to pad out the observing of the observatory. The idea with coordinated parallels, at least initially until we get our feet wet, is to focus on coordinated parallels that are really integral to the science that you're proposing. Okay, that's the key word. It doesn't appear anywhere in APT, but if you look at the policy documents, they're really looking for coordinated parallels in cycle 1 that will affect positively affect the science being proposed, not just, oh gee whiz, let's turn on MIRI because I'm looking with NearCam and see what's nearby. That's wonderful science, and we'll get there. But right now in cycle 1, I think we're really focused on the positive gain science from coordinated observations. I hope that's clear. Yeah.
Number 4 is not going to be available in 2503.
Okay, I'm told by Carla Peterson, who's our APT help desk, but also our, what do we call our moderator today. The world's expert on APT is sitting right here, and I'm talking in front of her, so this is already a scary experience for me. Anyway, number 4 here in this list is not quite there yet in the version of APT that was just released, and that will be coming along for cycle 1. Note that number 4 and 5 are not two-way streets. When NearSpec MOS is prime and NearCam is in parallel, we don't have a reverse mode where NearCam is prime and MOS is parallel. Same thing down here for NearCam imaging with nearest imaging. It's a one-way street. These others can go either way. NearCam prime with MIRI or MIRI prime with NearCam, for instance. Okay? Okay, I wanted to say just a couple of words about APT and ETC, which is the other main tool that people will be using. Klaus gave a nice talk last week on the ETC, and there will be another demo version of the community webinars coming up in a few weeks, I think, as well by Swara, and you'll be able to see the details of the ETC. That's where you come up with your exposure parameters that you need to put into APT. And so after experimenting some with the ETC, you'll have a lot of different runs. Some of them will be the ones you really want to transfer. That information in cycle 1 will have to get transferred manually over into the APT templates. We are in discussion about doing something more sophisticated in the future that would automate or partially automate this process, but that's not going to be there for cycle 1. So be aware of that. ETC is where you get your exposure information. Also, at some point in the near future, hopefully the target acquisition aspects will also be done through the ETC, so the information for target acts that you need in APT will also come from the exposure time calculator. Now this imposes a certain amount of bookkeeping on the proposer to kind of understand which of your calculations in ETC are practice runs and which are the ones you kind of focused in on for your actual observations. And also I just wanted to mention, this is one thing that I've noticed, that ETC is working at the exposure level, and if you're going to go into APT and then devise a dither pattern, so there will be multiple exposures, you kind of want to know that ahead of time. But maybe if you're just running the ETC and coming up with a signal to noise for an individual that you want for an individual exposure, what you really want to be looking at is how many exposures am I going to put in my dither pattern in APT, and then use that number of exposures back in the ETC to come up with your final answer. So there's a little back and forth that you should be aware of between the two tools, that if you think ahead a little bit and understand what you're going to do in APT, it will drive what you want to do when you're in the ETC. And I just wanted to mention that in passing. A little helpful hint there, hopefully. Okay, so I'd like to jump over and jump out of the PowerPoint here now and do a little demo of APT 25.0.3, which is the version that has just been released. I just wanted to note here on this chart that I'll refer to the top toolbar in APT, the tree editor, I'll call this thing on the side. I'm not sure if that's officially sanctioned language, but that's what I'll call it. And then the window here, I'll call the active GUI window or the active window, and the display in here changes as you select things in the tree editor or as you select different tools off the toolbar. And so with that nomenclature, I'll jump over to do the APT quick demo for you right now. Obviously can't spend too much time with it, but I wanted to highlight a few things. You can get APT, as always, right here. Again, HST and JWST, you download the same thing. They're both in the same tool. And also, with the questions that come up, there is the help desk now at this location as well that you'll be able to get questions for if you can't figure it out on your own. And there will be much, much more documentation becoming available for this within hopefully about a week. Everything is in advanced draft form, and we're just kind of getting the last comments taken care of and getting the approvals for the documentation to help you with APT, for a significant amount of documentation to help you with APT. That will be an ongoing process as we go forward as well. Okay, so I'm going to jump over to a different screen here, and this will be a little bit hard for you to see because the fonts are so small in APT, but I'll try to point where I'm talking about here. This is what APT looks like when you first open it up. And you can't really read this, but it says new document here. And so if I click that pull down menu, I get an option for either a new HST or a new JWST proposal. Today, to speed things up, rather than do that, I'll show you a trick, which is that you can come up to your top menu under File, and one of the options is JWST Demonstration Proposals. And I'm going to choose the one that says Mosaic Example. These last three in this list, by the way, have a little more meat to them. The first four are just each of the four instruments and each of their templates with entries in it so that you can see what valid templates look like for each of the instruments. But here, for the Mosaic Example, this one has a little bit more meat to it, so I'll load that one up, and you won't have to watch me try to type things into GUI boxes and whatnot. It'll all be here for us. So okay, so it comes up in the tree on the side here. We've got proposal information, and you can see these little arrows you can open up to see what's inside of each of these containers. Okay, for the proposal information, obviously there's the proposal description part. You can enter your COIs and PIs and so forth in the proposal information section. That's just like HST. For targets, you actually see I have a red X on targets, and that is because I have two targets in the proposal, but the new version of APT has a box that wasn't there before when the demonstration proposal was put in. It's asking you with this red X, if I hover over the red X, you get a little error message that says, oh, you have to enter a category. That's a new box in APT for this release, and when you've entered this one from the pull-down menu, you will, and I will choose Galaxy there, for instance. Now you have to enter descriptors, and there's a table of descriptors that you choose from, and I will call this a spiral galaxy. How's that? Just to make things legal and get rid of that red X. You can see now that the red X's have gone away on that first target, and I could do that on the second target as well, but I won't take time to do that right now. Now I've got a folder here that says observations, and I've got two observations predefined in here. These are mosaic observations of the galaxy M83 and M82. The first one here, we are going to be in what's called the form editor part of the tree here, and this is the display in the form editor. I wish this was, if I do can I make that larger if I do the plus X or the, no. I'm sorry that this is, the text is so small here. It's really difficult for you to see, I'm sure. Anyway, I'm sorry? Oh, it's not too bad from your view. Okay, that's just I can't see it. Okay, that's fine. Okay, so here we have, I'm not seeing all the details I expected to see here in the form editor. Oh, I have to open this up. There we go. Here's my two observations. There I am at the observation level now. This is now a NIRCam imaging template. So I've gone in here and selected NIRCam out of the pick list previously. And then I selected NIRCam imaging out of the possible templates in this list. And once those two are selected, now I am just seeing what is valid and interesting for the NIRCam imaging mode. As you click through other options, you would see this display down here change. For instance, not everything can use the mosaic tab, so the mosaic tab may go away for things that are not valid, but we can do mosaics here. As a matter of fact, we are doing mosaics here. So the first button here is your exposure specs. So I've actually come in here with the add button and selected some filters that I wanted to observe and so forth. That's how you add things. If I just said, oh, I really didn't mean to do that, I want to remove that, I can take it away again. Here's some exposures that have been defined. It's asking me for a module, whether I want the A or B side of NIRSpec or all of them, and I've said all. And then for that particular one, full is the only thing you can choose, but for one of the other options, for instance, for one mode or the other, you would actually, just a minute ago, that worked. What happened? Oh, on the B side, you can see you can choose various subarrays here in that pick list. So you can use these pick lists to do what you make the selections you need to make. I'm using NIRCam full field imaging to try to look at the Galaxy M83. I have defined in mosaics a 4x2 mosaic, and you can see that's summarized in the list down below. You can use these controls to change the amount of overlap between the tiles. You can use these sliders in the row and column shift to skew the mosaic if necessary to cover an object. Let's say your position angle on the sky was restricted by the target's position on the sky and for JWST constraints, and you have an object that you need to skew the mosaic to cover. You can do that with these controls right here. Now I can visualize this right off the bat, or I could go and run the visit planner on my proposed observation and see if that works. It doesn't matter what order. Let's try going to the Aladdin viewer, which pulls up a separate window. Here you can see now I've selected for this first observation. Here's my 8 tiles of the mosaic. And if I want to see what that looks like with the Palomar Sky Survey, the digital sky survey behind it, I clicked the wrong place. I am sorry. Thank you. I was trying to get here to say load DSS. And now you can see maybe you can see the galaxy back there behind. All the same things that kind of work for HST. If I wanted to rotate this and see what it, make sure, of course it's a fairly symmetrical object, so it doesn't matter, but I pull one tile and everything else follows it. And you can see what the rotation does for it. There are other controls here that do that. For instance, you can say, give me the coverage circles. I'm sorry I have to bop back and forth between the two screens, but there you can see as the field rotated around what would get covered by at different times of the year, depending on when the observation gets scheduled. So unless you have restricted the position angle, you don't know exactly what you're going to get there until the observation gets scheduled. But since it's a fairly symmetrical object, that doesn't really matter too much. Again, another thing is if I actually moved something, here I just moved one tile, but if you move the whole array, you can see that information pops up in APT. You can decide over here by clicking on that whether you want to commit that back into your the target position or not. And if you want to clear it, you can clear it, and you can see here that it's gone back to where it was supposed to be. So the Aladdin display is there for visualization. Just real quickly, if I actually jump over here and grab the other observation, which is the MIRI observation, you can see it takes many more tiles with MIRI to cover the same region, and I'm going to take that coverage circle away. Again, I'm sorry, I have to jump back and forth here. Sorry. There we go. And there's the MIRI mosaic pretty much covering the same region of the sky. So lots of controls there to play around with in Aladdin. But to get down to business, the main thing that you would want to do at this point, since I've defined an observation here, is to go to the visit planner. And again, You might notice here, by the way, that the orbit planner is grayed out. That's something that only Hubble uses. So when you choose the JWST side, the things that are not a bright object tool and orbit planner get grayed out, and you can't do anything with those. But here's the visit planner. And again, if I open up with a little arrow this observation, you can see there's my 8 visits. You can see that I've got yellow caution symbols on here. And if I hover, it tells me that this has not been processed since the last change. So you come down to the Update Display button. And if this is schedulable, I will get a green check. And I better get a green check. It does take a little while to run the visit planner, so don't be alarmed if this goes. The bigger the mosaic or the bigger the observation set that you are processing, the longer this step takes. Okay, so I got a green check. And even though I got a green check, I still wanted to show you a few things. If I open this up, you see at the visit level, and you can also open up at the individual visit level and see the individual constraints that go into the schedulability analysis. I obviously don't have time to go into all this. You can, see the words better if you play with the sidebars. By the way, the sidebar can also be moved if you need to. But this was schedulable, so that was good. With a right click in the visit planner, I get a little menu of things that I can do. And so, for instance, if I wanted to actually expand all the visits and out like that, I can do that with one click from the right click on the observation level. I can collapse it all back down again. But what I really wanted to show you is that there are 2 diagnostic plots that can pop up here. And I just only going to take time for one of them right now, which is to show you this one that shows the number of visits that have guide stars as a function of the observatory V3 position angle. This is essentially as a function of time, going across here as well. And since I have 8 tiles, you can see that it does come up, and there are 2 big windows of time where I've got all the tiles getting guide stars at the same time. That's good. That's lots of scheduling flexibility. We like that. If you didn't have to constrain the angle for science reasons, we have nice big windows to schedule this, and that's what we like to see. If I had gotten a red X, chances are there would have been one of the tiles, at least that there was no time where all the tiles got guide stars simultaneously, and you would see that this would max out at 7, for instance, instead of going up to 8, and you would know you have a problem tile. And by hovering over the green line, or I have to click maybe. Oh, the flat part? There it is. It will tell you, anyway, as a function of position across here, which tiles have a problem. There it is again, see? So you get diagnostic information as to which tile is causing the problem. There is a procedure you can then go to remove that tile from the mix and schedule it at a separate time, but still keep it associated with the rest of the mosaic. So that's just a quick look at one of the diagnostics that's in APT for mosaics, especially helpful. Okay, very quickly, just running over to M82 for a second. Notice that it's still showing me M83 over here until I go into Aladdin and tell it that I want to load the DSS again, and I will get my M82 picture over here, hopefully. Not take my click. I'm sorry, I'm still looking at M83. That's why it's doing that. So here's M82. I wanted to just highlight the fact that you have to click DSS, load DSS again to get the new target when you change targets. Here you see I've defined a mosaic now that is elongated along the major axis of the galaxy. If I wanted this to happen within some range of position angle, I would have to go in and use special requirements in the observation. So I'll come back over here to the form editor, and you can see in special requirements that I have added an aperture PA range that keeps the galaxy and the mosaic aligned at a reasonable level, but still provides some scheduling flexibility and so forth. So I could go on and on in APT. I hope that's maybe enough to give you a little bit of a flavor. These things control what you see in the active window. The tools up at the top control what you see in the active window as well. And using them together, you have a lot of power to enter and diagnose your observations. Submission button is up here as well, of course, making a PDF file, so forth, target confirmation charts. summary of the errors. If you want to see a summary all in one place, there are several different ways you can look at the error messages and get a summary of those as well. So that's a very quick tour of APT and where it stands at this point. I should go back. I meant to mention when I was looking at observations in the form editor, coordinated parallel button is right here. And if I click the coordinated parallel button, you will see the GUI change. It's a mosaic, so it took it a little bit. And so you get to select which mode you're going to work in, NearCam with what in parallel. You select it here, and then you will get different selections for dither patterns that are specially designed to handle the dithers for both instruments simultaneously. So that's the way you specify coordinated parallel observations. Okay, I think that was the last thing I forgot to show you. So, okay, so now I want to spend a little bit of time on target visibility tools. And yes? So are there a couple of questions about APT before I go on to the target visibility tools? Or do you want to wait till the end? I want to have 20 minutes for this, so I don't have too much time for questions now. If there are a couple, I'll be glad to.
So I have one question.
Okay.
And you might not know the answer, but I do.
Okay.
So the question is, will APT be able to show the coverage circle subject to the actual roll constraints of JWST, and when would that be added? Starting again, will APT be able to show the coverage circle subject to the actual roll constraints of JWST, and when would that be added? And we do not currently have a plan to add that.
There's a little bit of a back and forth between the visit planner. As a matter of fact, this segues very nicely into the next part. You can go into APT and define an observation, and then check the schedulability, and it says, oh, it's not schedulable. And for instance, if you constrain the position angle, maybe you chose an angle that JWST can't do, or it can't do it at the time that you requested it. That's a hard way to find out that it's not going to schedule after the fact, after you've added all this stuff into APT. And so one of the reasons that we have developed these target visibility tools that I'll tell you about next is to help you ahead of time kind of look at things like that and know what will and will not work when you go into APT. So hopefully it's a big time saver, and you don't waste time putting something into APT that turns out to not be schedulable because of something like the observatory visibility constraint. It just can't look at that angle for some reason. So I want to briefly talk about these two tools, the general target tool, visibility tool, and one for chronography specifically. Just say a word about why these tools are needed. Of course, APT does all the detailed schedulability constraints, as I've already discussed, but it's hard to get the overview information, and especially when you've got observations that may depend on one another for offsets in position angle or offsets in timing and so forth. You'd like to know what those visibility windows are, what the position angles are, so that you can plan, for instance, again, for chronography, very important sometimes to place the scene on the detector at a particular angle and get insight into that. So the target visibility tools that I'll tell you about are really, that's their reason for existence. They give you a quick look or a pre-planning ability that's just not there in APT, and hopefully will be a big time saver, especially for observations that have any kind of constraints on them. So a few examples. For instance, a TOO, a supernova goes off. Is it visible to JWST now? Is it right at the end of its visibility window, so I won't be able to follow it? I mean, those are kind of questions that you would want to know before you activated your TOO, and you can do that very quickly with the general target visibility tool. Timing possibilities for your NearCam pre-imaging compared to your follow-up MSA spectroscopy, for instance, depends on the length of your visibility windows. If you really want to push the system and get your MSA observations turned around, you want to see that your NearCam observations for the pre-imaging get scheduled early in a visibility window, and you have time to turn that back around. Otherwise, maybe you're 6 months off to the next window of visibility. This gives you some insight into what's possible there for your follow-up spectroscopy. Of course, the actual angle will be assigned by the long-range planner, but that's a separate detail. You can see what the possibilities are. Mentioned coronography, I'll talk about that a little bit more, but basically there's a lot of reasons that you have to avoid obscurations in the field of view of the instrument itself. You don't want to put your disc right along an obscuration finger or something like that, so you have to plan the angles very carefully to get your coronography observations to happen at the right time, and the coronography tool will give you the insight into that. And then really just basically anytime that you want to know if you have to constrain the angles of a mosaic or whatever for NIRCam or MIRI or anything, what are the available position angles for my target? The tools provide both visibility windows and looks into the position angle availability. So like I mentioned, there are basically currently these two tools. Both of them return the ecliptic coordinates of your target, and I just wanted to highlight that because most of us astronomers are not really that concerned with the ecliptic coordinates of our target. Galactic coordinates maybe, but not ecliptic coordinates. Well, ecliptic coordinates matter to visibility to JWST, and that's why we wanted to provide some visibility into that for your target. If you're having a hard time getting the right the angles that you wanted on your target, if it's at low ecliptic latitude, you're not going to be able to, to observe that target at that position angle. It's just a restriction of the observatory itself. And again, I'll try to show a couple of examples of high and low ecliptic latitude visibility just to give you some insight into that. I think it's an important point. So the two tools, general tool and the coronography tool, are available. The general tool is just a command line Python tool, but you will actually if you download the Institute's package called Astroconda, or they have just now come out with a version called Miniconda, so you don't have to download the whole 3 gigabytes. You can download a smaller portion of it. But you work in this environment that they provide, and then you just run this command. It's just basically the tool name, the RA and dec of your target, and this tool accepts both sexagesimal and decimal degrees coordinates for your target, and it will return then a table of the angles versus time for each of the 4 science instruments plus the observatory V3 and even the FGS the guide camera as well. By default it comes to the screen. It also then puts an interactive plot up to the screen by default. Both of those can be redirected into files if you would rather not run interactively. So for instance, for bulk batch processing, you can set up a bunch of these commands and then shoot them off and get output files instead of having it come to the screen. So that's why this tool is nice. It gives you a lot of flexibility to do different things. I'll show you there's a lot of command line options that you can add in addition to RA and DEC that allow you to control the outputs. Okay. So in this particular example that I'm showing, I've showed you that I've used the name flag to put the name of the target on here so that will show up on the plot and in the output file. Here's a save plot command that allows you to, on the command line, send this to an output file instead of to the screen. This is the plot that would show on the screen. It's all 6 instruments, and you can say, wow, that's not very useful because it's going over several years of time and it's got multiple things and I can't read the axes. That's fine. There are tools in the interactive mode that allow you to zoom in on these things. I'll show you that in a moment. Or you can restrict the time frame to be smaller than the default time frame for this and actually get these plots to show you limited time ranges as well. The ASCII file that comes out, I just wanted to highlight, so here you can save table to a file, you can save the plot to a file as well. The table, which spews out to your screen by default, and this part of the table down here is very long. There's 1 entry per day for all 6 instruments and the minimum and maximum angles for each of the instruments. As a function of a year or more, you're going to have a big long table down here at the bottom. At the top of the table, though, you see a summary for in this case, there's 3 big visibility periods. It tells you the overall length of the visibility periods. So this target has basically 1 per year, 1 long 200-day visibility period per year, and gives you the V3 position angle at the beginning and end of the window for those. But you get all this detailed information down here in the big table. Here is the ecliptic latitude. It repeats your target coordinates here as well. Okay, so that's kind of what the ASCII file looks like. You can restrict this to be just one instrument for the output plot instead of all 6. So if you were just interested here in the V3 position angle, in this case I've just selected the one instrument with a flag on the command line, and I'll just see the plot for the one instrument. You still get the ASCII table for everything, however. The chronographic tool is really run by the GUI window. Once you enter the command that starts the tool, everything else is done in the GUI window. I'll show you that. It's got a control panel and 2 plot windows. You can actually install this as an app, just like APT. You click on the app and it opens up the GUI and away you go. You can either enter an RAN deck, or this tool does have a convenient name resolver like APT does to enter the target, and it will find the coordinates from SIMBAD automatically. Now the chronographic tool is really just showing you what's going on with NIRCam and MIRI and with its specific chronographic masks. And so that's not the general tool you'd like, although many of the other instruments are pretty closely aligned with these two instruments. And so you can kind of use this for general purposes as well. If you like the pretty visibility plot that comes out of this tool better than the other, you can do that. But you have to be aware that the angles may be different for certain instruments, like MIRI is offset from NIRCam, and NIRSpec is quite offset from the rest of the instruments. Anyway, one of the nice things here is you can add companions to your primary target in the chronographic tool. If you have a disk, or if you know of planets that are around and you want to see where they lie on the detector relative to any obscurations, this tool allows you to do that. So it's pretty critical for those that are doing chronography. And so at this point, I would like to, and there's kind of what the output from the chronographic tool looks like. This is your control panel on the side. This is your visibility window. And then this is for the mask, instrument and mask that you've selected, this is the field of view of that particular instrument. Okay? And I'll show you that in a moment. Here's some companions have been added now, so you get tracks in the detector field of view that shows you where things are, and you can actually click on things in the display, and you'll see them pop up. The corresponding time pops up over in the visibility plot, or vice versa. You can click over here, and it shows where you are on the track over on this side. In this particular example, there's just one companion star, or companion planet. So I mentioned these tools are almost ready for prime time. They just haven't quite been released yet. The tools themselves are pretty much ready. We're working on the documentation and getting the final approvals to push that stuff out there, so it will be out there very soon. Again, you will have to, this is not my problem, but this is how the tools got instituted. You'll have to either load Astroconda or Miniconda from the Institute to just be able to use these command line tools. There are instructions that we link to from our documentation that will help you with that process. And again, the help desk is available for any problems you might have. It involves using the bash shell. If you're not using bash shell, sometimes you have to do some special things to get that all to work. And I apologize for that, but that's the way it is. The general documentation site is at this location. You will see things called JWST target visibility tools, or a helper file for each of the two tools will pop up in that documentation as soon as I can get approval to put things out there and we get things finalized. And with that, I think I want to quickly try to at least show you each of the tools if I can. So here is a window, that's the terminal window, but I've actually set this up in my I have Miniconda loaded on my machine, so this is the Miniconda environment on this window, and I can type in command line things, and I had some typed in from before, so you don't have to watch me type this again. But here's now the general target visibility tool, RAN deck. I've given it a name, which is of the high ecliptic latitude example, and I've set the time period to be 1 year starting at June 1st, 2019. And if I hit return, there's the big ASCII table, and there's the plot that pops up in the background. If I don't put that as a background thing, you have to click out of the plot in order to get your window back, or you can put it in the background and you can still access your window down here. But I can still scroll up on this window. You can see that for the year, it's given me 365 entries down here. Again, min and max angles for everything. Ecliptic latitude, 76 degrees. So this is up pretty high. And this is typically what the visibilities look like at high ecliptic latitude. You have one big observing window per year, and it's a very lengthy one as it shows here. There are controls for these plots down here in the corner, the home, forward and backward. As you start to archive multiple plots here, I'll show you that those go forward and backward through your plot stack. This one, the zoom, is probably the most interesting one, and you click to activate the zoom, and you can come in and highlight a piece you want to blow up, and it blows that one up. If I want to blow up something different in another plot, I can blow up something different in another plot. Each of the instruments themselves, so you can come in here to whatever level of detail you need to see things, to read off the axis. You are also getting in the lower right-hand corner the readout of the cursor as well, so that you can get values, exact values that way if you want to. The plot stack here, if I use the back arrow, you'll see I'll just go back through those plots that I just made, back to the beginning, or I can go forward again through those, or I can hit the home button and it puts me back to the default plots that I started with. Okay, so that's a little bit of that interaction. You can play around with the other buttons and see what they do. There is a save to a file button right here on the GUI if it gives me the words. It's not giving me the words, but that is the save file button, save to file there, and you could give it a file name. Okay. Let me now, so try to kind of look at that. I'm going to put that back to is it at the home? Yeah. So there's one long visibility period over a long period of time, and a very wide range of possible position angles that I could, for instance, put the near spec as a function of time during that window. So that's what you get at high ecliptic latitude. If I now close this out and run the low ecliptic latitude example, low ecliptic latitude, and if I come back to the top of my file, I will see this is at ecliptic latitude of 9.2, so we're down low. And now you see I have got two visibility windows. They're about 50 days long each, but neither of them goes over a very large range of position angles. This is basically an observatory constraint. JWST cannot roll more than that at low ecliptic latitude without exposing the cold side to the sun. So the angles are just simply at low ecliptic latitudes. They are restricted. You do get two values and about 6 months apart. So for instance, if I was looking at a near spec target, clearly I'm going to have a pre-image taken in one of these windows, and I'm going to have 6 months to get around to getting my MSA file back in, because the visibilities, you're not going to be able to probably turn it around fast enough to get it back into that same window. That's one possibility. But the other thing is, if I really wanted to observe this thing at 150 degrees of near spec aperture position angle, I can't do it. No time can I do it. It's just not available. And so that's why this target visibility tool, you'd like to find that out now rather than after you've entered this thing into APT and had a problem. So that's the kind of functionality that you get out of the general tool. You get all 6 instruments in one go, but you can investigate any of them in more detail. Very briefly, I want to just show you the coronography tool. Again, I've got the command loaded up here. It's just, there's the command that you run. This will be in the documentation, obviously. I'm going to run it in the background because it just pops up a GUI window. There it is. Make that as big as we can get it. Okay. So in this case, you can actually enter a target in here. I'll put STScI in there. And the search resolves the name and puts the coordinates in for me automatically. It defaults to the NearCam channel A and to a particular chronographic mask here. Let's just, for fun, we'll click that to show you the visibility part of this. Update plot. It's showing me the NearCam and that particular mask field of view over here. There's no obscurations other than the central obscuration here, but there are neutral density filters that are used as part of the target ACK and obscurations around the active part of the field that the tool shows you are present there. If we wanted to look at another, let's go to MIRI and maybe go to one of the 4-quadrant phase masks and run update plot again, you'll see that there's actual obscurations in the field of view that you will want to avoid putting. For instance, if you had a disk object, you wouldn't want to put the disk right along one of these quadrant edges type thing. So this plot is just the visibility plot, prettier one than the other tool provides, but it's the same basic thing. It shows you in red the solar elongation angles that are available. These are the available observing windows. There are 2 of them. Or one long one, I guess, since it kind of wraps around in this particular case. And then the blue lines are showing you the range of angles that are available at any given time. That's why it's a big fat line. And as with the other one, we've got the ability to come in here and zoom into a section of the plot and investigate those angles in more detail. For coronography, the range that you can offset at any given time is actually something you might want to pay attention to, for instance. You do have to click this tool again to turn the zoom mode back off again. And if I click, here I'll demonstrate it, clicking in here shows the north and east vectors over in the other field. If I then go in here and add a companion, and actually I can use this example to do this a little bit faster maybe. Here's 3 companions, and update the plot. Okay, I will zoom into this inner region so you can see that a little bit better. And you can see right now that if I want to observe those 3 planets around STScI, STScI doesn't have planets as far as we know, but I'm pretending it does, you're going to have a tough time getting them out from behind the 4-quadrant phase mask all at the same time, for instance, with that particular set of parameters. I did it quick, but you enter the PA from the main target. That's a standard east of north position angle of the planet, and then a separation in arc seconds, and you get up to three companions shown in the plot over here. And so if I wanted to say, well, at least I can get this one here, what time is that? I'm still in zoom mode, sorry. So I can click on that, and it shows me the time, the corresponding time over in the other window. If I wanted to use this window up here, that's in this other observing window, and or I could click over here, and it shows me where I am over in the detector field of view. So there's this functionality that just allows you to diagnose what you can and can't do before you get into APT. That's the main purpose of the chronographic tool. Okay, very brief. I know. I'm sorry it was so fast. If you have any questions, we have a couple minutes. I'll be glad to try to answer them. Nothing online? Any questions online? Any questions by people here in the room? All right. If not, thank you very much, and we will try to get out an email about the availability of the tools as soon as we have the documentation out there to support them. Okay? Thank you very much. Hope that was useful.